Smartphones are a technical marvel that allows users to exchange text messages, take photos, and access the internet. They are popular due to their portability, excellent computing capabilities, and low pricing. With the advancement of technology, every month new versions of smartphones are launched in the market. This makes the people lure towards selling their current smartphones and buying the new ones. In this tutorial, we will learn how to predict the price of these used smartphones using data visualization tools with a few concepts of data science on the Jupyter platform. So let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
Welcome to this case study session on used smartphone price prediction. In this session, we will analyze the data for used phones and build various regression models to predict the price of a used phone.
So during this case study, we are going to understand an application of regression techniques, which is to build various type of models. And we will also be performing an extensive EDA on it, right? So the case study is about, as I said, the refurbished phone industry, wherein, these days during COVID, everyone's trying to save some money. Be it on any of the unnecessary costs that people generally do. So there has been more focus on refurbished items, not just with mobile phones, but with also the automobile industry, we can say. It has been growing at a rapid pace. And this type of problem you can relate to any of the services wherein, it is coming from market, from some other owners, and people are buying it now just to save cost and to look for some more viable options and in a cost-effective manner. So there is a startup, let's say, who's trying to settle into the market, who's going to deal in smartphones mostly, and they are trying to understand the various factors which influences the price of a used smartphone. And we have some sample data for it, which we'll use in order to build various algorithms and to help that business price the phones effectively so that they don't end up with losses, right? So we want to look at the various features of a smartphone and then price them accordingly. So the data dictionary that we will be following today has 15 variables. Namely speaking, it starts with the brand name. So what is the make and model of the phone, right? Then the operating system. Then you have the screen size of the mobile phone. It's in centimeters. Is the mobile phone 4G supported? Is it 5G supported? Yes or no? Then what's the resolution for the main camera, the rear camera? What's the resolution for the selfie camera, the front camera, right? What is the internal memory? So the ROM, right? If it is 32 GB, 64 GB, 128 GB, what is the capacity? Then you have the RAM, the processing power of the phone, right? The battery in milliampere, weight of the phone in grams, the release year, in which year the phone was released by the manufacturer, then the number of days the phone has been used, right? The selling price of a new phone of similar make and model, and the prices are given in euros. So this is the data from the European nation. So you can say new price is the price at which a new phone is being sold, and used price is the price of the phone in the market for the refurbished one. So we're going to take a look at all these features, and this is going to be our dependent variable, which is used price that we are going to predict. So we have already gone through the data dictionary. Let's start by importing all the necessary libraries first. So as you can see here in the libraries, we are going to use linear regression. Then we will also fit decision tree regressor, random forest, adder boost, gradient boost, and then something called a stacking regressor, right? Stacking regressor is basically a heterogeneous ensemble of various models. Just like random forest, you can say is an ensemble, which is all the models in the background is cart, a decision tree. right? Similar kind of models. But stacking is if I want to combine, let's say, a random forest with an adder boost with a gradient boosting. That's how a stacking regressor works. So we'll take a look at stacking as well, which is a combination of various models to see if one of the algorithm is not giving result. Can I combine all of them to get a good result or not? Then we are also going to look at neural network and XGBoost, which is based on boosting techniques. So let's read the data, understand what is the shape and size. So there are about 3,500 observations we have with 15 variables in total. These are the variable names as we just discussed and the data that is available within those variables. So you can see the brand name, couple of names available here, which say Samsung, Sony, others, Vivo, LG, Apple, Asus, Realme, and all. Operating system, mostly you'd find Android, iOS, Windows, others. Then you have the screen size in centimeter. Is the phone 4G supported or not? Yes and no. Is the phone 5G supported or not? The resolution for the main camera and the secondary camera, which is your selfie cam. Then the internal memory in GB, RAM, again in gigabytes, battery in milliampere. Then you have the weight of the phone in grams, the release year, number of days the phone has been used, what is the price in euros for a new phone of same make and model, and what is the price of the used phone that it is being offered for. So we have this sample of about 3,571 observations, which we are going to use to build a model and deploy this model. If let's say if I get a good accuracy on it, I want to deploy this model too in order to get future predictions, appropriate prediction based on these features. So let's quickly look at the structure of the data. So we have in total 9 floats and 2 integers. So 11 numeric variables and 4 objects. 4 objects relates to 4G and 5G, 2 which are binary. So instead of yes and no, we can say this is ones and zeros. We're going to convert them into ones and zeros. And for brand name and operating system, maybe we can go ahead and create some dummy variables towards the end. So that's how we'll convert everything to numeric and then put model on it. If you look at the number summary, so for the numeric variables, let's suppose for some of the important aspects of a phone, like the resolution of the main camera, we have a minimum of 0.08 megapixel and a maximum of 48 megapixel. So it clearly shows there are some phones here that are available, which are feature phones, not really smartphones, right? Just like you have some featured phones which are available within 1,000, 2,000 rupees in the market, where you don't get much of a clear camera, right? And these are budget phones, we can say. Same with the memory. So you have some phones which does not have any internal memory. You have to add a memory card in order to use those phones, right? And phones as high as 1 terabyte of memory. For the RAM as well, these basic feature phones does not have any sort of RAM. And the maximum we have here is 16 GB, right? With battery 80 mAh minimum and a maximum of 12,000 mAh, right? The least year is 2020. So let's say if we are in 2021, so the earliest available phone is 1 year old at least, and the maximum is 8 years old. Where the newest phone available is 91 days used, and the maximum is more than 3 years. The average price of a new smartphone is 109 euros. And the average price of all the new phones in this data is about 237 euros. So we can get an idea that the phones are approximately priced 50% or less, right? If you look at the describe of the object variables, so we've got 34 unique brands in this data with 4 unique operating system, majority of the observations being Android phones, with most of the phones are 4G supported and majority of the phones are not 5G supported because 5G is not yet available in all the countries. So let's say if 5G is available limited areas, then there will be only a couple of phones which are going to be using 5G. For that matter, in India, let's suppose in India also, we don't have a 5G band available. There are a lot of phones that are 5G supported already, right? So similarly, we can say that this data might be for that duration when 5G just announced or is going to launch in future in those countries, and people are expecting to buy a 5G phone too. So by looking at this summary, we get some idea about the distribution and about some of the outliers, if there are any. Let's go ahead and analyze them in a univariate, bivariate scenario where we plot and understand what are the most significant factors that affect the price of a phone. So what we can do is, in the bivariate standpoint, I can use price as one of the variables, and I can compare it with the rest of the independent variables to understand the impact of each one of them, whether they are going to be a significant predictor or not. But before we do that, I'm replacing the yes and no in 4G and 5G with 1 and 0. So I'm replacing yes with 1 and no with 0 in both the variables. So now if you look at head, there are only two variables which are strings. Everything else is already numerical. So let's go ahead and look at the distribution of these two categorical variables, which is string. So first of all is the brand name, which is 34 unique brands, and we can see others is dominant, which means not categorized in the list here. And the most available phone after others is for Samsung, and then Huawei, LG. So we can say these are the top 3-4 brands that captures most of the market, right? But you can see there are a lot of other brands as well. And the minimum ones are OnePlus, BlackBerry, Microsoft, and all. Probably because these phones do not have much wide range. They have like a couple of models only. But coming to Samsung, Huawei, or LG, they have a lot of models to choose from. So people prefer to choose from different models, and that's why they have a higher market share, right? Related to the operating system, majority of the phones dominant on Androids. Then you have others like some OEM specific softwares like Huawei. Google has banned Huawei to use Android. So they have come up with their own operating system. Similarly, Samsung also, for some of the phones, they use their own operating systems. They don't use Android or Windows. Then you have Windows predominantly used in Microsoft phones and also used by Nokia a lot. iOS used by Apple only. So there are only 56 phones in the market out of 3,500, which is Apple, which shows that people are not ready to sell out their Apple phones that easily. They are very satisfied with that phone and they want to keep them and using them. Okay, so let's go ahead and look at visualization. First, I'm going to compare the used price against the new price to understand the relationship between them. And this plot giving us a very good idea that if I'm going to buy a new price, or I'm going to buy a phone with a higher new price, the used price of that phone is also going to be higher. So there seems to be a very good linear relationship between the two. This would turn out to be a significant predictor. Now, when we say we want to build a model, generally, one tip that I want to give you all is analyze and use those features which you are going to see in testing data. Now, there will be some data sets where some of the data points will be added post the prediction, right? Let's say I take a different example, let's say of a loan default. I'm going to analyze the customer's information like their credit score, their age, and their transactions, their previous loans and all. And then I'm going to decide whether I want to give them a loan or not. Let's say I decide to give them a loan. Now I also am capturing what is their tenure of the loan, because I've given them a loan. What is the amount of loan that I have given them? Now, these two variables, if we have in the data set, are you likely to see those in the test set? Test set means in future, if you want to screen an application for loan, are you likely to see the tenure and the approved loan amount? No, because that will be added post the decision has been taken to give them a loan. So those two variables, although a part of data set, are not going to be very useful for building a model because you will not get any observations for it. So you need to identify such kind of variables in the data and then remove them from the data set first, because those are not likely to be present in your future observations. And that is where you have to think about the data a lot, that, if you have 15 or 20 features, which are the features which you are likely to see in coming future, and just keep them only, right? So new price is one of the features we can say that will always be available. So if I'm going to market to buy a used phone, I would know what is the price of the same phone for a new one. So this is going to be a very significant predictor in order to understand for the used price. And we have already seen the relation, right? New price or the used price is almost half of the new price. And we'll validate that once we do the prediction. Let's go ahead and look at some of the other features. So if we compare the used price with the number of days the phone has been used, we see there is no such relationship right? There's not much of relationship within the price bucket of 250, we can say. So this range, if you look at this highlighted range, there's no such relationship. But if we look at the relationship here, above 250 euros, there seems to be some bit of positive relationship. That if the number of days used is increasing, it seems that some of the price is increasing, some of the price is decreasing too. So there seems to be a mixed trend, right? We can identify the relationship directly by just calling out a heat map or saying what is the correlation between these two values. That will give us a better idea. But from the plot, it looks like a mixed relation. More or less, we can say it's not going to be that significant as we have new price, because it clearly shows a linear relationship between the two. Similarly, for the year of release, we can see there is some trend with the most recent phones fetching a higher price, phones from a very past fetching a lower price, right? Understandably, newer phones will give you a higher price and old phones will give you a lower price. Then if you look at the weight of the phone, not so much of great relationship here. We can say it's kind of a random scatter. Doesn't matter what is the weight of the phone, the used price might not be related to weight. If you look at battery capacity, again, the same thing. Seems like some of the positive relationship. If the battery is increasing, used price is also increasing, but slightly, not that great. This is from the RAM. Again, doesn't seem to have that much of relationship. We see that the highest prices that we've got is for these three buckets. If the phone is from 4 to 8 GB, we can say maximum number of phones fall into this bucket and you get higher price for them with respect to the others. If you look at the internal memory, again, the same. Most of the concentration that you have is within 200 GB, and some phones which offers a very high memory as well. Selfie camera, most of the concentration you can see within 10 to 25 megapixel, right, which has a higher price for used phone. Not good of a relationship, we can say. It's kind of a random scatter too. With respect to the rear camera, the main camera, we see some relationship. So the price is more when the rear camera has a higher capacity or has a higher resolution. With respect to the screen size, again, we see some positive relationship going on where the screen size is increasing, the price is also increasing, right? Some bit of relationship. And finally, the operating system. So we see that the price is almost similar in case of iOS, others, and Windows. We can see like the normal range is from 0 to 750 with some outliers in Androids. Whereas Windows phones does not fetch you higher amount of money. So if someone's selling a used phone which is based on Windows, it will not give them the value for their phone, probably. With iOS and Android has a good distribution. And with respect to brand, so we can see here, Apple being one of the brands is getting the highest prices for the used phones. Huawei is also one of the market leaders wherein they are dominating the market in the used phone space as well with a higher price range, right? Then you have Oppo and Samsung also getting good price. The ones that are not getting price is all the local brands. With Microsoft adopting Windows, you can see the used price phones are very less. Let's look at an average price of all the brands. So we see the average price available in the market for all the phones is the highest for OnePlus, which is above 300 euros, and followed by Apple and then Google. So the highest value that on an average a phone is fetching is highest for OnePlus, followed by Apple. And the same case with operating system, if you see, the highest average price is for iOS, which is above 250 euros. Android on an average is available within 120 euros. Windows is available within 50 to 80 euros. And the other phones, other than these three operating system, is available in less than 50 euros. With respect to 4G, if the phone is 4G compatible, the average price of all the phones is about 140 euros. When the phone is not compatible with 4G, it's only going to fetch you about 50 euros. So there is a very big difference if the phone is 4G supported or not. There's a big difference in the price. And similarly for 5G, you can see the cost went up to 400 euros when the phone is 4G, 5G supported. And if it is not, then the average is about 100 euros. So for 4G, the phone is available with within 150 euros. But if the phone is 5G supported, it is available for more than 400 euros because these might be the latest ones in the market. And the most recent phone will give you a higher price as compared to the old phones. Okay. So if you look at which brand offers what type of operating system, this gives us a very good market share. That Microsoft is one of the brands which has adopted only Windows operating system, with Apple adopting iOS and others. So in some earlier versions of maybe Apple, they might have used some of the other operating system, or might be this is some data entry error. But if you look at some of the brands like Coolpad, Gioni, Google, or let's say Infinix, Carbon, these are all Android-based phones. They do not adopt, or they do not have any model which is for a different platform. With Nokia has an equal share of Android and others, and with some share of Windows too. So this gives you a market composition of what brand is accepting what type of platforms for their phones. Finally, if you look at the correlation between all the numbers, because this is where we will be most interested. If you are going to build a regression model, probably for linear regression, you don't want our data to be highly correlated because that will lead to a problem, multicollinearity. So if you look at the relationships within the data here, the maximum that I can see is maybe 0.74, which is battery and screen size. If the screen size increases, battery increases. The next best is available under release year and selfie cam. So the more latest phone, the higher the resolution of selfie camera. And then there is 0.93 as well here, which is between new price and used price. So this was the first of the plot that we saw, right? 93% correlation between new price and old price. So the most significant factor that influenced the price of a used smartphone is going to be the price of new phone of that same make and model. So if I'm going to buy, let's say, an iPhone 10, and it is available in some euros, the price of the new phone at that time for iPhone 10 would highly impact it. So we can say this is one of the major criterias of identifying the price of a used phone, right? New phone price. This is going to skew the result a lot. And then we have battery, screen size, selfie cam, and all. But there is no such multicollinearity issue as we can say, right? Relationship with the dependent variable is fine. Within the independent variables, we don't have anything above 0.75. Even we have only two pairs, which is 0.7. So you can say the data is still good. There is no problem multicollinearity here, right? Now moving on to some data cleaning steps. If you look at the number of missing values, we have 180 missing values in the main camera and small number of missing values in some of the other variables. This is the major one where we have 118 missing values, which is contributing to approximately 5% of the overall data. 5% is a significant number, so we can't really calculate a mean or median of the overall data and replace it, these missing values with it. So what I'm going to do here is first understand where are those missing values and which brands, and then probably take a brand-wise median. So if I group by brand and look at the median of the main camera. So for Acer, the median resolution is 5 megapixel. For Alcatel, it is 5. For Apple, it is 12. So I've calculated a median for all the brands. And then what we are going to do is, for wherever there is a missing value, that brand information is available because it has zero missing value. And based on that brand, I'm going to replace it with the median of that particular brand. Rather than just taking a median of overall, I'm going to look at brand-wise information and then impute it accordingly. So I group it by brand name and then transform. Basically, I'm filling in a lambda function to fill in the missing values based on the different brands we have. And then if you look at the missing values, there are still 10 missing values in the main camera. And the reason could be that for Infinix, as you can see here, they have models in the market which do not have a camera available, or maybe for all the observations of the Infinix brand, the main camera was a missing value. And that is why we still have some missing values here. Now, since this is going to be a very small number, as you can see, it is less than 1%, right? 0.2, 0.3% and all. I'm going to replace them with the generic median now. So I say, go ahead and replace it with the median of the overall data. And then if you look at the number of observations, it's all 0. If I want, I can also remove these observations because there are very less number of observations. The main point of concern was replacing the missing values with their respective brand names, right? I've not taken a standard median value, but grouped it by a brand name. And then based on those brands, I've imputed the missing values. Right? That's one of the good ways to do it, right? Whenever you look at some data, rather than having a standard operation on missing values, in the last industry session, I showed you how you can use pipelines and avoid data leakage issues. So you can use that to fill in the missing values. And if you want to do a quick analysis, this is also some of the other ways that you can use, right? Now let's look at the distribution and outliers for all the numerical variables. So I've selected only the continuous variables from the list. So it seems the screen size is right skewed with a lot of outliers on both the ends. With the main camera has some outliers, which is why the data is skewed. And again, it looks like a multi-model data. Selfie cam, again, there are some outliers because of which there is some skewness. The internal memory, there are huge outliers, right? RAM, again, we can say this is one of the discrete value, really not a continuous value. Battery, there are some outliers again in battery as well. Weight of the phone, days used is probably one of the only variables where we do not have any outliers in it, but the distribution is skewed and it's kind of a bi-model data, as you can see. And the new price is also skewed. Let me also include the used price just to understand the distribution of the used price too. So if we run it again, the dependent variable, which is used price, is also heavily skewed towards the right. Now, you might have learned that during or while building a linear regression, if your dependent variable is highly skewed, you are probably not going to satisfy all the assumptions related to it, right? Like the residuals will not follow normality. Maybe the residuals are also not going to be homogeneous, or you can say it will not follow homoscedasticity, right? There might be a good pattern between the residuals and the predicted values. So in order to avoid all of that situation, we transform this generally whenever we are trying to build a linear regression. So we can transform it using a log scale, an exponent scale, or we can do a box-Cox transformation. But since we are going to fit other type of models too, we are going to look at the application of linear regression with comparison to the other modeling techniques, right? That do we really have to build a linear regression if the data is not supporting linear regression facts? Because if we also look at the correlations here, there is not much of correlation with the dependent variable. For the used price, which is the dependent variable, the independent variables does not have a high correlation except for the new price. After new price, the highest correlation that we see is for days used, which is 47%. And that's a negative relationship. The more number of days the phone is used, the lower the price is. And then everything is less than 0.5. Probably 0.5 is RAM and 5G. But we see that there is not much of relationship, right? There's no significant relationship as such. So linear regression might not be a good fit for this kind of data because there is no significant linear relationship between the dependent and independent variables. So we'll see that if linear regression gives us a good fit or not. But let's just quickly remove these outliers first. So we have outliers in almost every variable except for days used. So what we are going to do is cap the boundaries. So I say wherever there is an outlier outside the upper whisker, cap the value at upper whisker, or if there is an outlier below the lower whisker, cap the value at lower whisker. Right? It's a standard outlier process that we will follow. So I create a user-defined function to calculate the first and the third quartile, and then calculate the upper level and the lower level at 1.5 IQRs. And by running a loop on all the variables where we had outliers, I'm going to cap it there. So all the outliers now being treated with all these values that you have are capped at whiskers. So two of the most important data pre-processing steps or data cleaning step, which is to impute the missing value and outlier treatment, has been done. Let's go ahead and now prepare the data for modeling. So we create our X and Y's, which is a list of all the independent variables and the dependent variable only. So I'm going to use these 14 variables that you have here as independent variables and one variable which we are going to use for dependent variable. For brand name and operating system, because these are still characters, I'm going to create dummy variables for them. So the data now looks like this, which is dummy for the brand names and the operating system and some of the numeric features that were already there in the data. And then I go ahead and split it into 70-30. Right? Now, this 70/30, we are going to build various models on. I'm going to fit the training set to build the model and will validate it on the test set. So starting with linear regression, right? Let's see how it performs. So we fit the linear regression on the training set here. And if you look at the coefficients of all the independent variables, you'd find that coefficient of some of the variables is very high and for others is very low. For example, let's say 120 for 5G. So if a phone is 5G supported, it automatically, based on this coefficient, fetches you 120 euros more, right? With every gram increase in weight, it's saying that the cost or the price of the phone also increases by 0.16 euros. For every release year increase, the price increases by 5.7 euros. For every day use of a smartphone, the price reduces by 0.10 euros. So you can read the coefficients and understand which are the most important coefficients here. If you look at the intercept, it's minus 11412. So it's a negative. Intercept is just a constant. We don't really read this number just like we do for slopes. If we go ahead and predict it on the training and the testing set both, let's look at the R-square value. So the R-square value that we are able to achieve on the training set is 73% and on the test set is 78%, which seems to be an okay model because anything above 0.75 is considered to be a good model. And we are able to achieve 75% on the test set, and the difference between train and test is still within 10%. So I can say it's not overfitting or underfitting. It's a valid model where we are able to achieve close to 80% accuracy or 80% of variance explained in the used price with respect to all the independent variables we have. Let's evaluate on the basis of RMSE. So what is RMSE? It is root mean square error, right? So read it backwards. Error first. What is error? Error is nothing but the difference between actual and predicted value. And then you take a square of those errors, because if you take a mean of all the errors, they will cancel each other. That is why we take a square of all those errors and then add all the errors to calculate a mean. And then we take a square root of that number. So RMSE in general represents what is the average error in your model. How far is your actual value and the predicted value on an average. So it says the error in the training set is about 63 euros and in the test set it is 53 euros. So which means if the price of the used smartphone is 100 euros, I'm predicting it with a variance of 53 plus minus euros on the test set, which seems to be a very high value, right? If we look at the model diagnostic, this is predictive analytics. Now we are moving on to diagnostic analytics. What is diagnostic analytics? Basically, whatever you have built as a solution, you validate it. But then now you want to understand what is the impact of your model on the data that is there. That is diagnostic analytics. So I create a data frame of only 3 variables, which is the actual data, the predicted data out of the model, and what is the residual, the difference between the two. And then I'm comparing the predicted data against the residual, which gives us an idea if the model has homoscedasticity or not. So here we can see a clear trend that as the predicted price increases, the residuals or the error in the model goes down and the predicted price is below 0 as well. You can see there are a lot of observations for which the predicted price is less than 0, because this is a coefficient based model. Based on the coefficients, you are likely to see negative values too, which is not true in case of real world scenarios. Can you have a smartphone with 0 or less than 0 price? Which is not possible. It should always be greater than 0. And this is where the dependent variable that we had the skewness in it, right? There was a lot of outliers on the upper end, and because of which there was a skewness. This is the result of that. That linear regression is not giving us a good fit. And also we also saw from the heat map where there was no correlation as such between the dependent variable and the independent variables. Although we are able to get a good R-square value, RMSE is also a good way of understanding the accuracy, which is very high error at the moment, right? And the plot also says that we are predicting okay within a price range of 100 to 200 mostly, right? The residual is very close to 0, but post 200, if the price of the predicted phone increases, the error in the model increases a lot. So one of the assumptions that the residual should follow normal distribution. If we plot the residuals, see, it's not following a normal distribution. Because of the skewness in the original data, you see a skewness in the residuals too. So linear regression is not able to satisfy the assumptions here, we can say. And that is why, even though it has a good R-square value, I cannot use this as a production model. And that's one of the shortcomings of linear regression always. So being the oldest concept available, being the first predictive model to be ever built, linear regression is not that applicable to real world scenarios these days because of the complexities in the data. The relationship is not linear anymore. You'll find weird patterns. You'll find nonlinear relationships for which you can do regularization using L1, L2 penalty terms, which is lasso and ridge regression. That might give you a better result than linear. But again, if you don't have that correlation between the variables, it's going to be very difficult to get a good result in regression terms. That is why we have those other algorithms that model the data in a different way, like decision trees. It doesn't look at the absolute values. It discretizes the data in the background and then builds a hierarchical structure to model it. So within decision trees, you can say it's a parallel processing, might have a higher prone to error and overfitting. That's why you can also try boosting techniques, which is XGBoost, AdaBoost, gradient boosting and all, which works on sequential processing and gives you better results than what a parallel processing does because it optimizes the results automatically, right? And the same case with neural networks too, because of the back propagation, which is optimizing the model by adjusting the weights and biases again and again. It gives you the most accurate model that is possible, right? So now after linear regression, let's go ahead and compare all those models on the same data and see what are the results. So I'm going to start with random forest first. I've taken some of the randomly chosen hyperparameters. So I'm saying that the max depth of the tree should be 10 levels, 10 branches. And the minimum sample split as 50, which means I should have at least 50 observations in a node in order to consider it for a split. And I fit the training set to it. Let's look at the predictions for random forest. So if you look at the score, which is the R-square value, we've got a very high R-square as compared to linear regression, which was around 75%. Now we've got an R-square, which is around 85%, which is a 10% improvement, a big difference, more than 10% improvement in random forest as compared to linear regression. Now, with this improvement that we have, let's see if we are able to reduce the error. We have been able to reduce the errors too. With 58 euros as a root mean square error in linear regression, we have dropped down to 41. And with the difference between two, we can say this is a valid model. Right? And there are no such assumptions that we need to validate when it comes to random forest. Just like in linear regression, you have a lot of assumptions that you need to validate. There's no such assumption in random forest. Again, random forest is also not impacted by the noise, which means it doesn't have any impact of outliers. It doesn't have any impact of the relationships in the data. So it's one of the most preferred models when it comes to real life values because it models the noise very easily. It is up to us to tune the model properly. If you don't tune the model properly, then it is a, what you say, hungry model, or we can say this is a greedy algorithm, which means it overfits very easily, right? So optimization of the hyperparameters is very important. So you can define some of the random numbers, look at the accuracy, and then probably also use grid search in order to optimize it further, right? Try different values and see how the result changes. And then pick the one that is giving you the highest accuracy. If you look at the same pattern that we saw in linear regression in case of random forest, this gives us a very good result as compared to linear regression, where we see that the price is more than zero. First of all, a good check that at least we are predicting a positive value. And then up to 200 euros, it seems the error is almost negligible. Up to this point, right, there is the residuals are on zero line, which means for low cost phones, this model is very accurate. There are not a lot of residuals. Then up to 400 euros, there are some residuals which are close to the zero line. We can say up to 50 or less than 100 euros of difference. But post 400, which is for higher end smartphones, the price is getting really high, or the error we can say is getting really high. So whenever we are recommending a model to the business, we are not just going to say, okay, I've achieved an RMSE of 40 euros. I'm also going to give them this insight that the model works very accurately up to a point of 200 euros. From 200 to 400, this is my error range. And post 400, it's not good. So ideally, I should be using this model in order to predict prices for low-end phones, not for high-end phones. Because for high-end phones, there is a high variance in all the other parameters. That's why we have a lot of noise in the data and high errors. But for normal range phones, it's giving us a very accurate result. So you can probably use this in predicting the price for low-end phones. If you look at the feature importance, because random forest has also one of the good thing that it can give you the variable importance. Now, based on this variable importance, if we see the highest important variable is the new price, which is about 80%. So 80% of the splits that has been taken, or 80% of the overall Gini gain that you have in the random forest is because of new price. And from the ED as well, we understood there was a very good linear relationship between the new and the used price. Also on the correlation matrix, it was 93% correlation. So understandably, this is going to be the most important variable. And then the number of days used, which is 15%. So combine these two is 95% of importance, which means if I exclude everything else and just look at what is the new price, what is the price of the new smartphone currently, and how many days it has been used, these two variables should be able to give me the price of the used phone. These are the two most significant factors. Doesn't depend on brand, doesn't depend on operating system, doesn't depend if it has a 4G or 5G, but it depends on the number of days the phone has been used and what is the price of the same phone in the market currently. Those are the two most significant variables coming out of this analysis, right? Let's try and fit some of the boosting algorithms too to see if we are able to further improve the results. So I'm fitting adder boost again with some random hyperparameters and predict using the same. So the R-square value that we've got here is even better than random forest. On the training set, we've got 98% R-square, and on the test set, we've got 89%. It's approximately 10% difference. We can say it's 9.7%, which is very close to 10, but still considerable. Random forest gave us an 88% R-square on test. This is giving us 89%. So a bit of improvement. But let's see if this improvement also improves the RMSE or not. The RMSE drops down to 38 euros or from 41, which is again a significant dip. If you look at the same residual predictions, right? Now you see it is also predicting price greater than 0, which is good thing. Up to 200, this also has a very low residual. All the residuals are close to the 0 line. And up to 400 as well, it does not have much of a residual. As in random forest, we saw there was a residual of 100 euros and there was a higher scatter. You see, there is a lower scatter in the higher end models. If I scroll back to random forest, you see the highest residual that you have is going up to 600. And on the lower side, it's going up to minus 200. Here, there is one outlier which is going below 400. But on the upper side, it's mostly within 400 euros or mostly within 200 euros on the positive side. So most of the observations, most of the smartphones you have here is within plus minus 200 residual range. So you can probably say slightly better than random forest, if not extremely better, but at least something better than random forest. If you look at gradient boosting, another form of boosting, the R-square drops. And if the R-square is dropping, understandably, the RMSE increases, right? And if you look at the same plot, it's giving you a pattern, which means it's not one of the good models. If you fit a MLP regressor, which is an artificial neural network, so let's say I'm just using one layer. Within one layer, there is 8 neurons, and then I'm using ReLU as the activation function, rectified linear unit. So you can see here, at every step, this is optimizing the error in the model. At the first iteration, second iteration, it is adjusting those weights and biases. And it will keep on reducing it for the number of iterations we have defined. So we have said build 20,000 iterations. And if there are no change in 1,000 iterations, then stop the process. So it is going to check for 20,000 iterations and keep reducing the loss. We started from a loss of 21,349 units and we have dropped down to 400 and still optimizing, right? So while this is running, let me take one of the questions. Should we treat outliers and null values before doing univariate analysis? So the answer is no, because univariate analysis is done on the data as is. Univariate analysis gives you an idea of what should be a data preparation step. It helps you understand the distributions and everything that will help you to take a decision of what measures to use in case of understanding missing values or how to use outlier treatment. Because there can be various ways in which you want to do that, right? So univariate will give you a better understanding of it. In the meanwhile, this algorithm has converged. So it has taken 10,000 iterations and the loss has been reduced to approximately 425. Let's go and look at the performance of this model. So the R-square value is pretty high, but you can see here the R-square for train is very high as compared to test. This is overfitting, right? We can reduce the overfitting by adjusting the parameters here, but in the interest of time, I'm not doing it. You can run a grid search in order to optimize the parameters, use different solvers. Instead of Adam, use stochastic gradient descent. Instead of ReLU, use the other activation functions like 10H. You can use linear, right? Change the iterations, change the tolerance level, and see if you are able to get a good result. And since it is an overfit result, you see the RMSE is also very high. And if you look at the patterns, pattern-wise residual is almost the same as we saw in the boosting algorithms, where the price prediction starts from negative values. So some of the observations you can see is breaching the zero line. So some of the values are predicted negative because this is overfit model, it is not fitting the data properly. But on the residual side, almost everything is up to 300 euros is very close to zero, on a negative side mostly. And up to 400, there is like similar kind of scatter that we saw in the boosting algorithms and random forest. But residuals goes as high as more than 600 euros on the negative side and on the positive side too. If you look at XGB, which is your XG boost, and 99% accuracy on train and 89% on test. Again, close to 10%, we can say, we can consider this as a valid model, but almost 100% accuracy on train, which means there is a lot of scope of optimization on the hyperparameter side. Let's look at the result. So this also gives us an RMSE of 38, which is what we also got with ADA boost. And if you look at the residual analysis here, see for XG boost, up to 400, the residuals are very close to zero line. For the rest of the algorithms, we saw up to 200, it was close to zero. And then after 200, there was a lot of errors between -100 to +100. But with XG boost, this is probably the best of the result that we have received so far, right? Where we see that up to 400 price range, we are getting a good prediction, which is mostly zero residual. Post 400, again, for higher price points, higher error. And mostly on the negative side, which means we are predicting high when the actual value is low. So this probably has the best result so far in terms of the residual analysis. Now, since we have understood the performance of individual models, let's quickly go ahead and build a ensemble, which is to combine all of these models together into one. And the most popular ensemble is a stacking model, where we say that from a data set, we build individual models first. So I'm going to create a base learner. This is called the base layer, right? This is where I've fitted random forest, add a boost, XG boost, gradient boosting, linear regression, 6 different kind of models. What we are going to do with stacking is we take the first layer, which we already have, predict out of those layers, put the predictions into another model, and then use that for final model as the predictor to predict the values. So I'm going to create 2 layers of models here. One is called the base layer. This is layer 1 and this is layer 2. So the first layer is the individual models that we have fitted now on the original data. The second layer is going to be fitted on the output of the previous layer. This layer will not be built on the original data. This is going to be built on the predictions from the previous layer. And then I'm going to use this layer 2 model as the final model to predict the actual values out of it. This is called stacking ensemble. Right? You can have more than 2 layers if you want. And the number of algorithms in the base layer can also be 4, 5, 6, whatever you feel, right? So what we are going to do is, on the base layer, we are going to consider these 4 algorithms, which is the gradient boosting, the neural network, AdaBoost, and the random forest model. And since XGBoost gave us like a very good prediction on the residual side, I'm going to consider XGBoost as the final model. So the output of all these 4 models will go into the XGBoost model as an input, and from XGBoost we'll get our final predictions. Right? So I'm creating those estimators, and then from the stacking estimators or the stacking regressor that we call from sklearn, I'm going to fit this data. Right? So this is going to create this structure where it will first look at these 4 models, predict from the 4, use those predictions as input for the final layer, and from the final model, we are going to finally predict the values. So it's going to take like a couple of minutes in order to fit it, because we are also doing a 5-fold cross-validation here, just to make sure there is no kind of biasness in the model. In the meantime, this is running, I can take a couple of questions. So one of the questions that I have is, can you tell us when and how to impute missing values with mice and KNN, and how it will differ from mean median? So theoretically, when you are using a mean or a median approach, you are generally imputing only a single value, right? If the number of missing value is more than 5%, that's what I personally use as my benchmark. Wherever there is a variable with more than 5% values, I will not impute it with mean or median, like a standard. In today's case study as well, you see for 5% missing values, I looked at the missing value brand-wise. For respective brands, I imputed the missing values differently. I did not take a standard median of that variable and imputed it directly, right? So out of all those 180 missing values we had, there were different values imputed, not a single value. So mean and median it can be preferred when there are very less count, probably less than 5%. If it is more than 5%, then it is preferred to use techniques that I showed today, which is to look at group-wise median or mean and impute it using that. Or you can also use KNN for that matter. KNN, I showed you in the previous industry session too, that you can use it on both numbers and categories, right? And you do it after you split the data in case of train and test split, right? So there is not much of a difference that you will see as far as the overall result of the model goes. If the number of missing values is very high, let's say 20%, 25%, in those scenarios, you would find some differences. And it is always preferable to use KNN when there are very high count of missing value. If it is between 5 to 10%, still I can use mean median grouped by the other data points we have. But if it is more than 10%, probably an algorithm like KNN is going to give me a better result. Why are we removing outliers? So this is a standard process, right? Even though a random forest does not have any impact of outliers, so we do data processing only once, right? So we've taken a best practice of standardizing the data so that it can be fit to any model. So the objective was to fit multiple models. That is why we treated outliers. Otherwise, we could have taken 2 copies of the data, one only for linear regression where we have done outlier treatment, and another one which is no outlier treatment done for random forest or for the boosting algorithms, right? Any approach is fine. There's no problem with imputing outliers for random forest too. Can we treat outliers in dependent variable? No. So dependent variable, do not ever do any type of treatment on the dependent variable. If there are missing values, go ahead and remove those observations. Do not impute missing values in the dependent variable. Do not do any sort of treatment or outlier treatment on the dependent variable. If it is skewed, you can try transformation, like convert it to log scale, convert it to exponent scale, do a box-Cox transformation. That is something that you can do on dependent variable, but no outlier treatment, no missing value treatment. If there are missing values, remove those observations. That's the only rule. Do not try to impute it. If there are outliers, try transformation, not outlier treatment. In stacking, are there any considerations to choose base learner? Similarly, what are the considerations to choose the final meta learner? So in stacking regressor, as you see that the base learners are very important, the first layer, because based on the result of the first layer, the final model will be created, right? So you will follow the same approach that I did today, wherein you fit the model to 7, 8 algorithms, understand which ones are working the best on that data, and then choose within that. Choose maximum, let's say, of 4 because if you take more, then it is going to be more complicated and your model will be easily overfit. So try to take 3 to 4 models in the base layer, the first layer, depending on which algorithms is giving you a good result while analyzing individually. Take them as the base layer. The best performing model, you can keep it as a final layer. Right? Choose like the 5 best performing models. The best one, keep as the final layer. The 4, you can keep it as base layers. Right? I'll just wait a couple of more minutes for this to finish. It's about to finish, I guess. It is still optimizing the neural network, as you can see, because on 5-fold cross-validation, it is running the process iteratively. Can you explain again when to treat outliers and when not to? So for outlier treatment, algorithms like random forest or decision trees are not impacted by the presence of outlier because it discretizes the data in the background. So the magnitude of the values does not impact the outcome of the algorithm, right? But for algorithms where a distance calculation is involved, like say KNN model, or even if you're doing k-means clustering, right, where distances are calculated, algorithms like LDA, which is linear discriminant analysis, again based on distances. So these type of algorithms are going to be impacted by the presence of outliers, right? Coefficient-based algorithms like linear regression, logistic regression, these are also going to be impacted by the presence of outliers, right? For that matter, neural network too will be impacted by the presence of outliers because of the calculation of weights and biases. It takes into account the magnitude of the values. So for these type of algorithms, you will always do an outlier treatment before building the model. And for decision trees, random forest, kind of boosting algorithms, they are not that impacted by outliers. So you can leave outlier treatment for these algorithms. Right, it's about to finish, I guess, last iteration. So for the diamond example here, it is not going to distort your equation for a very simple reason that how many observations will be like that? It is going to be probably less than 4 to 5%. And if you have such anomalies in a very small percentage of data, it's not going to skew the result of the overall analysis, right? So take it from those point of view. Can we remove outliers instead of capping it? So ideally, yes, you can do it, but then depends on how many observations you'll end up removing in that case, right? If you want to remove outliers from the data, then you will have to check multivariate outliers. What we did was univariate outliers. We looked at individual variables and identify outliers only in that particular variable. There are also ways in which you can deal with multivariate outliers, right? So multivariate outlier treatment is done using a lot of algorithms that are present. One of the algorithm names that I'm going to give you, you can explore on your own, is isolation forest, right? Go ahead and search for isolation forest. It is one of the best algorithms available to identify outliers in the data and remove them. So it gives you an observation-wise detail that which observation is an outlier as compared to the other observation. It doesn't look at one variable, it looks at all the variables at once. Okay, so the model has converged here. Let's go and look at the performance of the stacking regressor. The RMSE is pretty good. The R-square value is pretty good. 94% train, 87% test. Within 10%, we can say the model is valid. If you look at RMSE, it's 41, which is again similar to what we got with random forest, but not as good as AdaBoost, where the RMSE was 38. If you look at the residual analysis, it also gives us the similar kind of result, wherein up to 200, it says that the residuals are very low. Up to 400, there's a little higher scatter, and above 400, it's very high. So it's similar kind of result that we also got with AdaBoost, with XGBoost, random forest. Now, if I have to compare all of them, so what I'm going to do is create a data frame from the accuracy of all the models so that it can be compared at a single place. So all the accuracies that we have been seeing so far, I was saving them in a separate object. As you can see here, I'm saving the RMSE in an object. I'm saving the R-square value in an object. And similar to this, I've been saving it for all the algorithms. And finally, I'm comparing all of them in the form of a data frame. So this gives me the summary of everything that we have done today. We have fitted 7 different models. This is the training and the testing R-square values. This is the training and testing RMSE values. And then I've calculated the difference in score, which means what is the difference between the R-square value of train and test. And this is sorted in the ascending order of the differences. So we see the difference in the random forest model was the least, which is about 1.5%, where the test set was 87% R square and the RMSE was 41. Even the difference between RMSE of train and test was more aligned, followed by linear regression, where the test R square and the RMSE was very high. So we can exclude this from our conclusion, right? The next best was 38 RMSE and 89% R square, but the difference was approximately 10%. Now, if I have to take a call between random forest, AdaBoost, or XGBoost, I would prefer random forest for the simple reason it might be slightly on the higher side of RMSE. The R square values are almost comparable. We can say 87, 89, there's not much of a difference, just of 2%. But the difference in the train and test set is very less, which means this is more consistent on seen and unseen data both. AdaBoost and XGBoost is performing with a range of 10%, almost, on the words of overfitting or underfitting. Random forest is more stable, we can say, more aligned and on both the sets. So out of all the algorithms here, I will pick random forest as my final model. And if I have to recommend this to the business, I'll go back to random forest and say that this model is giving us a very good prediction up to 200 euros phones. From 200 to 400, there is slight bit of error, which is less than 100 euros. And after 400, we cannot use the model because the error is too high. With this predicted values from the random forest model, I have just looked at the residual analysis. I can also go back and see what is the impact on each of the independent variables. When I predict the price, when I'm predicting it very high, how is it the predicted price is compared to the actual price of the phone? How is it related to the number of days used? So you'll see all of those as a diagnostic analytics. And basis whatever is the result, you go back with the recommendations accordingly. So this was like a case study on regression analysis based on different models to predict the price of a used smartphone. So we identified two factors which are most important. One is the price of the same phone which is in the market right now. And second is how old that phone is, how many days it has been used. Those are the most significant factors in deciding the price. And if we know this, we should be able to predict the price with a 95% accuracy. That's what random forest is saying. These two are 95% important. After that, you have the internal memory, the weight of the phone. The only brand name that is coming up as a higher importance, which is less than 1%, but still with respect to everything else, it's Xiaomi. Probably Xiaomi is because it's the world's leading smartphone company right now. And then 5G, because obviously people want their phone to be compatible with the upcoming technologies, right? Some of the important factors that decides the price of a phone. And I specifically explained how to do diagnostic analytics today.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.